last packet in the rotation unit. This is chapter 11, 11.9 to 11.11. Conservation of angular momentum. Right? We've looked at all the other linear mechanics things we've had. So then we had conservation of momentum. Now we have conservation of angular momentum. We studied angular momentum in the last chapter. It's I omega, or R cross P. And so now we're going to look at how this is a conserved quantity. Okay, and same idea as before. Whatever the angular momentum is before, that has to have the same angular momentum afterwards. And our first example, this is just a bunch of examples here. It's a simple concept, but we need to practice applying it. First example, we have a 2 kilogram mass, and the angular momentum is given by this function. And so now we're asked to find the torque. Well, torque is dl dt. So all I have to do is take the derivative of this function. And so I get 6ti minus 4j kilograms meters squared per second squared, or Newton meters, however you want to put that. Right? It's already in vector form because it has the unit vector notation. As for 11.10, that slide there, that's just saying that if we're looking at an individual particle and then we take a lot of particles and put them together, then we get a rigid body. So the angular momentum of a rigid body works the same way as the angular momentum of a lot of tiny little particles that are just added up together. And so the total angular momentum is equal to I omega, where I is the moment of inertia of that rigid body. Okay. So for this, we have a uniform disk. So it's uniform disk, by the way, that means I equals 1/2 mr squared. And I want to know the angular momentum of the disk about the origin for part A. So for A, L equals I omega. We can do these as vectors for now. And so this is going to be 1/2 mr squared times omega. Right? So that is 1/2 6.5 kilograms times R, which is 0.4 meters. 0.4 because 0.8 is the diameter. Be careful about that. And then omega is 3 radians per second. Okay, and actually I don't have this calculated out, but if you set it up this way, we've got to square that. Whatever number you get, that's what to do. This is the more important part. Anyway, for B, now we want to know what would be the angular momentum of this thing about an axis that is 18 centimeters from the circumference. So if we're coming in to some new axis here that's 0.18 centimeters from the circumference, then all I have to do is apply the parallel axis theorem. It works the same way. L equals I, let's call this new axis Q, IQ omega. And so to do IQ, I just apply the parallel axis theorem, which is going to be the 1/2 mr squared plus mh squared times omega. So like before, it's 1/2 6.5 times 0.4 squared plus 6.5 kilograms. H now is 0.22 meters. And this whole thing gets multiplied by omega, which is 3. And whatever this turns out to be, that's the number. And actually, we don't have a direction here, and so we can't do these as vectors. In example 3, we imagine we have a meter stick on a table, and it's rotating around the table, and it's got this piece attached to the end of it. And we want to know the angular momentum of this thing as it goes around at a rate of 4 radians per second. So first, it's rotating around the center, and then if it's rotating around this end of the stick. So for part A, again, L equals I omega. And so now I have two I's, right, two objects for which I'm finding the moment of inertia. First one is going to be this stick, so it'll be 1/12 mL squared, right, where L is the length of the whole thing, so that's 1 meter, L squared, plus, and now this piece, which is, I think we're assuming that to be just a point mass, so that'll just be mr squared. And r is the distance, right, this half distance, so L over 2, which will end up being 50 centimeters or 0.5, times omega. That's it. Again, this is the important part. The setup, after this, we're just plugging in numbers, where little m is this, L is 1 meter, and this m is 0.4. For part B, again, L equals I omega. This was about A, this was about axis B. And so again, the only way this changes now is that this is 1/3 mL squared. And now this one is a distance L away from the axis. It's not just half the distance, it's the full length there. So mL squared, and again, times omega. Plug in the numbers, and but again, that's just calculator work. Getting this set up is the important part. Okay, so this example is a solid sphere rotating about the z-axis. The x, y, z coordinate axis has been set up this way. X is out of the page, y is that way, and then z is up. And so it's rotating vertically, you could say. And so we want to know the moment of inertia about the z-axis, rather. And so we're looking for the angular momentum about the z-axis. And since we know that it's rotating this way, we can find the direction, so we can do these as vectors. I is not a vector, but omega is. Right, it's 3 radians per second around this way, so it's positive in the positive z direction. So I, again, what is this? This is a solid sphere, so it's 2/5 mr squared. And then we'll multiply that by omega. The rest of this is just plugging in numbers, and I believe you get 4.5 kilograms meters squared per second. This one I actually have solved, right? This is 15.5 and 3. And so this ends up being, we can say, positive 4.5 kilogram meters per second squared. Or we could say up, right? Because it's in the, if you curl around this way, it's in the upward direction. Okay, and now again, conservation of momentum is related to Newton's third law. And Newton's third law, conservation of momentum hold even for rotation. So if I have something spinning around and the net torque is 0, then that means I must have constant angular velocity or angular momentum, right? Because 0 is the net torque. Well, that's equal to dl dt. That means that if I have 0 net torque, that means the slope of the L versus t graph is a straight line. It's flat. 0 slope, that's the net torque. And so the angular momentum has to be constant. And let's take a look at some examples. In example 5, we see this person sitting in a spinny chair holding these weights, and he's spinning slowly, pulls it in, and then he speeds up. So what we have here is I initial omega initial equals I final omega final. He's changing his moment of inertia, right? He's moving the weights, and therefore he's changing the velocity. And so that means omega f is simply the initial moment of inertia over the final moment of inertia times the initial angular velocity. And if this is, right, he's reduced the moment of inertia, so this is smaller, that's going to make the whole thing bigger, and he rotates faster. That's what you see with ice skaters do that. My high school physics teacher told us a story where they got kicked out of a bowling alley because they were sitting in the spinny chairs and holding bowling balls out, and they pulled the bowling balls in. They spun so fast they were falling all over the place, and they got kicked out of the bowling alley. Don't try that, but after you graduate, maybe we can go do that for bowling together. Okay, and then the ratio kf over ki in terms of in terms of these things. Okay, so ki is going to be 1/2 I omega I squared, and kf is 1/2 IF omega f squared. But omega f is this, so we have 1/2 IF and then I over IF omega I, this whole thing squared. Okay, what happens here? We end up with 1/2 I initial squared omega initial squared over IF. And we have more kinetic energy than what we had before. Somehow the kinetic energy has increased. How does that work? Well, this person has done work in pulling those things in. In pulling those weights in, he's doing work, he's increasing the kinetic energy. So notice, kinetic energy is not constant. Angular momentum is constant. But the rotational kinetic energy here is changing because there's work being done in the system. The astronomy connection is there. As solar systems and galaxies form, they start off as just these large clouds of dust and gas, depending on whether or not it's a second generation solar system or something like that. And as gravity is pulling on these things, there's rotation. And as gravity pulls things in, the objects rotate faster. And you'll notice that in our solar system, all the planets and the sun, everything is spinning in the same direction. Right? That angular momentum has been conserved. Okay, and so example 6 is one of these astronomy examples. It says here, our sun makes one revolution every 27 days. If the sun were to collapse into a neutron star of radius 20 kilometers, so much, much, much smaller than what it is now, what would be its new angular speed? Okay. And so we know that we've got I initial omega initial equals I final omega final. Now I want to know what would this new thing be, and so omega final would be I over IF omega I. Okay, let's look at what these numbers are. The initial is, we're going to assume that it's a solid sphere. It's really not, but we're going to assume that it is. This is 2/5 mr squared. Okay, this is initial. And then at the end, it's a smaller solid sphere, 2/5. Still the same mass, though. Let's assume that it hasn't lost any mass. So if it's the same mass, and then RF squared, and then omega initial. A couple things happen here. We can cancel out the mass. We can cancel out these fractions. So now I need to know RI squared over RF squared and omega initial. The thing about omega is that I don't know what it is in radians per second. I need to find the angular velocity. So it makes one revolution every 27 days, right? But we convert this to, we know we have 1 day is 24 hours, and 1 hour is 60 minutes, and 1 minute is 60 seconds. And so when we do this, we end up with 4.29 times 10 to the negative 7th revolutions per second. And then I multiply this by 2 pi radians for every revolution. And I get omega to be 2.69 times 10 to the negative 6th radians per second. So that's omega. Omega I, I should say. And so now I'm going to have, 6.98 times 10 to the 8th squared over 2 times 10 to the 4th squared. That's the initial radius over the final radius. That's going to give me uh, 21 or 132 radians per second. Some of my notes are a little funny here. I can't quite see. But again, the setup is what's important. And that means it's spinning about 21 times per second if we do that calculation. This is how neutron stars were discovered, by the way. As they spin, they're giving off radio waves, and they're so regular. They come very, very quick. 21, spins every second. And when they first discovered them, they discovered these radio waves that were coming in, and they were very regular. And the astronomers first labeled it LGM1, the signal LGM1, because they thought it was little green men. But they discovered it's actually a neutron star. It's a star that had collapsed, and as it collapsed, the mass collapsed down. It spun much, much faster, and it produces these very regular signals that astronomers can pick up. And for example 7, you can see that we've got 2 masses on the end of a rod, and it's spinning. Calculate the initial kinetic energy of the system. Well, K is just going to be 1/2 I omega squared. And so I here is going to be 2 point masses, treat it that way, 2 mr squared times omega squared, which is 0.8 squared. So I plug in some numbers. I kind of started doing that already. So those cancel out. M is 0.1. R, this is, it's a 1 meter rod, so that's 0.5 is R. Square that times 0.8 squared, and I get 1.6 joules. Oh, sorry, this is 8. 8 radians per second, so that's 1.6 joules. Okay, and then B, I want to know what is the new angular speed at the end once it's been pulled in. And so I know omega F, as I saw it in the other problems, is going to be I initial over I final times omega initial. That's just conservation of angular momentum. And so it's going to be this thing, the 2, because I've got 2 masses, mr squared initial over 2 mr final squared times omega initial. Plug these in. The masses are the same, and so Ri squared over Rf squared. This is 0.5 squared over 0.25 squared times 8. Okay, and that's going to give me 32 radians per second. Okay, and so now I want to know what's the final kinetic energy. Okay, so K is 1/2 I omega squared. And And so that's going to take this same form really and end up being mr, the new r squared times the new angular momentum. So mrf squared omega f squared. M is still 0.1. R now is 0.25. Square that. And then 32 is the new angular momentum. And so K ends up being 6.4 joules. Again, notice the kinetic energy is more. Why? Because there's been work done. An internal mechanism has done work and pulled those things in. So in this problem, the system is the student and the stool and this thing together. Right? And this thing is spinning. It's sitting there at rest. And this is spinning. And so the moment of inertia of the student, or the angular momentum of the student, is 0. But this thing has angular momentum L naught at first, right? But then he reverses it, flips the thing upside down. And so then now over here, this is now negative L naught because it's in the opposite direction. And so because it's a vector, I have to account for that somehow. That means that the student has to then take on 2L0, right? 2 times the angular momentum that this thing had initially. And that's why that trick works, and we'll do that in class, where you take the spinning bicycle wheel and you turn it, and the person in the chair starts turning. And voila, now like magic, we're in a new room, change my clothes. For example 9, in this one we have a rod that has mass, and these 2 masses at the end. And we want to know initially, what is the angular momentum when it's spinning at angular velocity omega? And so L equals I omega. And we can figure this out for each of the objects. We just add them up. Angular momentum of the rod plus each of the point masses that we have. And so this is going to be, I for the rod is 1/12 ml squared. For the rods, these are moving in a circle, perpendicular to the radius then. So sine of 90 is 1. So I can just do RMV, and R is L over 2. So I'll do L over 2 times V plus L over 2 M1V. But V is going to be the same for both. It'll be R omega, so L over 2 omega. So I can plug that in. I get 1/12 ml squared plus L over 2 m2 L over 2 omega plus L over 2 m1 L over 2 omega. Combine some stuff here and factor out, and I can take and let's see. Oh, this should have omega in it. Sorry about that. So omega, I can do L squared omega over 4, and then I'm left with just big M over 3 plus M2 plus M1. Right? And that's the angular momentum when it has angular velocity omega. The next part of this, we want to know what's the torque when it has angle theta given by that. Right? And so we know that sigma tau equals I alpha. Rather, we want to know alpha. Right? And so this is going to give us alpha. So I need to add up all the torques, and that's the torque from each of the objects. The rod is going to have 0 torque because the center of mass is the place where it's rotating. But these will each have torque. This will have positive torque. This one will have negative torque because this is pulling it clockwise. This one's pulling it counterclockwise. And so this torque is R cross F. R is L over 2. This one's going to be negative. And then F is going to be m2g, but then the angle, what's the angle going to be? We need to be a little careful here because here's the radius, and then here's the force. The angle we have is this one over here. It's not this angle, it's this angle. And so, if I make this over here, this is perpendicular, this is theta. The force is cosine of theta. So it's actually cosine of theta. And then plus, it's the same thing for this one. L over 2 is R cross F, so R m1g cosine of theta equals, and now I plug in I, the moments of inertia of all three things. So that's 1/12 ml squared plus m1 L over 2 squared plus m2 L over 2 squared. Just treating them like point masses. All of this times alpha. And now I'm solving for alpha. So all I'm going to do is take this and bring it under here. So this is going to be, let me rearrange this and factor some stuff out. So this is going to be L over 2 g cosine of theta, m1 minus m2. That's this side. I factored out L over 2 g cosine theta. And then over here, I can factor out 1/4 L squared. So L squared over 4. And then in here, I'm going to have m over 3 plus m1 plus m2. Let's factor some things out. So this goes out with that. 4, and I'll be left with a 2 down here, but that can go up to the top. So this will be 2g cosine theta, m1 minus m2, over m over 3 plus m1 plus m2 times that value. And that's it. Okay, in example 10, we have a student moving from the outside of this rim to the inside as this thing is spinning. And so we want to know what's the final angular velocity after the student has made it from the rim to now 0.5 meters from the center. And from before, in an earlier example, we had seen that omega f is I initial over I final times omega initial. So all I have to do is put in the moments of inertia initially and finally and multiply that by omega I at the end. So the moment of inertia in the beginning is the moment of inertia of the disk, which is 1/2 mr squared plus mr squared, because we're going to treat the student as a point mass. That's the student, and then starting off at the rim, so that's the radius initially, over the moment of inertia of the disk does not change, but the moment of inertia of the student does change because now the student is not at r, the student is at 0.5 meters, right? R is 2 meters. And we multiply that by omega initial, which is a 2. All you have to do is plug in the numbers now, and I believe that when you do that, you get 4.1 radians per second.